Hello everyone. This video is about DC to DC buck converter. Buck converter is a step-down converter, which means the output voltage is less than the input voltage. In buck converter, there are two modes of operation. When the switch is on, it is called mode 1, and mode 2 is the mode of operation in which the switch is in the off condition. L and C are used as the filter components, and the buck converter consists of a switch, a diode, L and C, and the load. And the switch is operated with a duty ratio of K is equal to T on by T. The buck converter can be operated with a closed loop in which the output voltage is taken and it is compared with a reference voltage, which is given to a control circuit whose output will be a PWM signal given to the switch. The two modes of operation are given here. In mode 1, the switch is in the on condition and D is in the off condition. During this mode, the inductor stores energy. In mode 2, the switch will be opened, turned off, and the D is turned on. The inductor, which stored energy during the mode 1, it is going to dissipate its energy. The waveforms for the buck converter during mode 1 and mode 2 are depicted here. The first one is the PWM waveform. Second one is the inductor current waveform, which varies from I minimum to I maximum. The third one is the switch current, which is equal to the inductor current during its on condition and is equal to 0 during its off condition. Then third one, the switch current and the source current both are same here. Then the third one is the diode current, whose value is equal to the inductor current during the mode 2 and is equal to the 0 value during the mode 1. And the capacitor current is equal to this. This waveform is the capacitor current. The capacitor current can be found by subtracting. The capacitor current can be written as IL minus I0. I0 is taken as the constant current, and the last waveform shows the capacitor voltage waveform. During mode 1, we can write the inductor voltage as L into dIL by dt, which can be written as Vs minus V0. Because the inductor, it is connected here. This side the voltage is Vs and this side the voltage is V0. Therefore, we can write VL is equal to L into dIL by dt equal to Vs minus V0. This dIL can be written as del I divided by T on, because the variation in the inductor current, it takes place during the inductor current rises from a minimum value to a maximum value during the on period. So we can write dt equal to T on, and dIL can be written as del I, which is equal to I max minus I min. So we can write L del I by T on equal to Vs minus V0. And we can rewrite L del I by T on as KT, because T on is equal to T on by T is nothing but K. So we can write T on equal to K into T, which is equal to Vs minus V0. And del I can be written as Vs minus V0 into KT divided by L, which is taken as equation 1. And we can also write KT equal to del IL by Vs minus V0. Where K is the duty ratio, T is the switching period, and T on is the on period of the switch. In mode 2, which is the time interval between T on and T, we can write the inductor voltage as equal to minus V0 because Vs is disconnected from the inductor. So we can write that VL can be written as L into, instead of dIL, we can write minus del I, because during mode 2, the current falls from maximum value to the minimum value. So we can write, we have taken del I is equal to I max minus I min, but for mode 2, dIL will be I min minus I max. So we can write dIL equal to minus del I. So dt can be taken as T off. So L into minus del I by T off can be written as minus V0, which can again be rewritten as, instead of T off, we can write T off can be written as T minus T on, which can be written in terms of duty ratio as 1 minus K into T. Therefore, L into minus del I by 1 minus K into T can be written as minus V0. So substituting that, we get del I equal to V0 into 1 minus k into t divided by L, which can be taken as equation 2. Also, we can write 1 minus k into t equal to del I L by V naught. This is taken as equation 2a. And we need to find the average output voltage. The average output voltage and the ripple current we need to find out. The average output voltage can be found by equating the equations 1 and 2. That is, by equating the time, equating the equations 1 and 2, we can find the output voltage, average output voltage expression. So equation 1 is Vs minus V naught into Kt by L. That should be equated to equation 2, which is V naught into 1 minus k into t divided by L. So equating and simplifying the expression, we get V naught is equal to k into Vs. So the average output voltage of the buck converter is k into Vs, and the k can take its value from 0 to 1. So V naught can take its value from 0 to Vs. So we can obtain the output voltage as varying from 0 to Vs. So we can vary the voltage V naught less than or equal to the input voltage for the buck converter. And in order to derive the ripple current expression, we need to take capital T, that is time period, equal to T on plus T off. We using the equations 1a and 2a, we can write T on as kt plus 1 minus k into T, because T off can be written as 1 minus k into T. So substituting for kt and 1 minus k into t using equations 1a and 2a, we can write t is equal to del I L divided by Vs minus V naught plus del I L by V naught. Simplifying this, we get del I equal to Vs into k into 1 minus k into capital T divided by L, from which we can write the value of L equal to Vs into k into 1 minus k T divided by del I, or we can take this capital T, that is time period, to the by substituting t is equal to 1 divided by f, where f is the switching frequency, which is equal to 1 by t. So substituting that, we can write del I equal to Vs into k into 1 minus k divided by fl, from which we can write L is equal to Vs k into 1 minus k divided by f into del I. Where del I is the ripple current. From this, we can find the have the expressions for ripple current del I as either this equation or this equation. So, which is a function of the L, that is inductance value, and the frequency. So now we have to find the ripple voltage expression. Ripple voltage expression can be written as del V equal to Vc minus Vc of 0, which can be written as 1 by C integral Ic dt plus Vc of 0 minus Vc of 0, or we can also find del V in terms of del Q. So del V can be written as del Q by C, and this del Q can be found by using the current inductor current waveform. So for this portion, if we find del Q, this portion, this length is nothing but del I by 2, and this base width is approximately equal to T by 2. So by applying the triangular, if we get the area of this triangle, that will give us the del Q expression. So del Q is half BH, that is B is nothing but T by 2, H is nothing but del I by 2. So half T into T by 2 into del I by 2 divided by C is nothing but the del V expression. So which will be equal to del I T by HC, or we can write T as 1 by F. So del V is equal to del I by 8 FC. From this, we can write the C value as del I by 8 F del V, and substituting for del I expression, we get the del V expression as like this, and from which we can also get the capacitor expression as like this. So this is the equation for either this equation or this equation can be used to find the ripple voltage expression, and similarly the C can be found either by using this equation and this is or by using this equation. So we have the design equations for L and C. Now, condition for continuous conduction. The continuous conduction will happen for the values of L and C if the values of L and C are more than a particular value, critical value known as the critical value of inductance and inductor and capacitor, which are denoted by LCR and CCR. These values of critical values of L and C can be found by equating the ripple current to 2 times the load current and ripple voltage to 2 times the load voltage. So derivation of LCR and CCR are given here. So del I will be equal to, substituting for del I expression, that should be equated to 2 times I naught. We can write I naught is equal to V naught by R. So we get Vs into K into 1 minus K by FL equal to 2 into, substituting for V naught as K Vs, we get 2 into K Vs by R, and rearranging. For this condition, L will be nothing but, the found value of L will be nothing but the critical value of L. So LCR will be equal to R into 1 minus K divided by 2F. This is the critical value of inductor. And similarly, to find CCR, we can equate LV equal to, expression for LV if we substitute, that should be equated to 2 times V naught. Rearranging this expression, we can write CCR equal to 1 minus K divided by 16F square L. This is the expression for critical capacitor value, where R is the load resistance. So in this video, we have seen the operation of the buck converter in 2 modes, and then we have drawn the waveforms for 2 modes, and we derived the expressions for output voltage, that is average output voltage, ripple current, ripple voltage, L and C values. Then we also derived the expressions for critical value of inductor and capacitor. Thank you.